Let us head over to the next talk then. Our next talk has again two speakers. So I welcome our next speakers. They are Jörg Lessig is the first speaker. Jörg Lessig is a professor for enterprise application development. He has graduate degrees in computer science and computational physics. He holds a PhD in computer science. He has had research and postdoc positions in Stanford and Berkeley and Lugano. And he is the founder and CEO of the I&M Institute for Sustainability Management. So welcome, Jörg. The second speaker is Maximilian Selch. Maximilian, he studied mathematics at the Dresden University of Technology, and he joined the Fraunhofer Institute for Machine Tools and Forming Technology, IWU, in 2020, where he leads the Institute's quantum computing project. So welcome, Maximilian, as well. We are looking forward to your joint talk on the topic of quantum Bayesian networks for path accuracy in manufacturing. The stage is directly yours. Welcome.
Yes, thank you very much for the nice introduction. And welcome also from my side. I'm very happy that we can present here about quantum Bayesian networks for path accuracy in manufacturing. And it's first me giving a broader view about our QAP Center mainly, which is the umbrella for different institutes working on quantum computing topics. And then I will hand over to Maximilian. So here on top, you see different application fields, production energy, integrated circuits, knowledge engineering, which are important for us at the QAP Center for Applied Quantum Computing Saxony, which is kind of the central initiative in Saxony with the focus applied quantum computing. Can we go back for a moment, please? I just want to quickly say also a few words about our institute. So here in the talk, we have IWU in Dresden, which is a main institution in efficient production, intelligent manufacturing, cognitive manufacturing. And we at the IUSB AST are more on the energy and water infrastructure side. Cybersecurity is an important topic. And of course, quantum computing. Yes, so let's now get a bit into the details. And the QAP Center can be seen as in two sides. One side is the focus on industrial applications, and there the clear goal is that quantum computing should become a game changer in different relevant applications in the different industries. We are going to implement pilot applications, detect the problems that can be addressed with quantum computing. And in order to do this, of course, we need the research and education side, where the goal is to educate the persons who can work in that field and to implement also the research in more foundational quantum computing. So I think now we can look quickly at two focus fields, and the second will be then already relevant for the more technical part of the talk here given by Maximilian. So this focus field, energy systems, is more covered by the Fraunhofer IUSB. It's about energy markets, energy management systems, and you see the scenario on the left side, the energy market with different entities, combined heat and power, heat pumps, car sharing. And on the right side, you see different directions where you need also computational power, settlement of the transactions in energy management, for instance, learning in the energy management system, and also planning tools for districts and dimensioning of districts, for instance. And of course, it is of great value to have here quantum computing to solve hard problems. Maybe we come now to the second focus area, which is about this digital twin scenario focus on manufacturing. And if you look at this scenario, you see different manufacturing steps, and you see that there's measurements in between, data which is coming in, and there may be uncertainties also in those measurements or measured uncertainties on the parts. And then you want to react to this. You want to react already in the next processing step. And of course, that's also welcome to have effective computational models and algorithms in this digital twin scenario. You can do some data aggregation simulation in between. And in the end, you can handle this manufacturing process in a way that you have, in the end, more good parts and have, for instance, improved modeling accuracy for simulations in between to be here more effective. So in this digital twin scenario brings us directly to our technical part of the talk, and Maximilian Selch will discuss now quantum Bayesian networks in one specific digital twin scenario. So Maximilian, I hand over to you.
Thank you, Jörg. And now we come to the topic of path accuracy in manufacturing. And as an exemplary manufacturing process, we deal with a 3-axis milling operation and see an item traverses a chain of various production steps, which consists of different milling and drilling operations. And the aim of each single process step is to perform an ideal processing, which is specified by a certain target geometry. And on the one hand, we have the fact that each mechanical process can cause deviations individually. And on the other hand, there are also cumulative effects. But here we want to focus on the effects of the individual process steps and want to find out the strength of influence single factors have on the quality of the manufacturing process. And this provides the basis to do a quality analysis of the holistic process later on, which is our long-term goal dealing with this manufacturing application. So of course, there are various approaches to tackle this task. And for various reasons, we decided to work with Bayesian networks to model the fundamentals of the underlying process and to estimate the strength of influences. So Bayesian networks have basically some nice advantages, such as the possibility to learn on a limited basis of information, to also work with incomplete data, and we can weight the certainty of our statements. So first, I'm going to briefly introduce how Bayesian networks help us in, so to say, the classical or conventional way, and then we discuss the basics of how to do this the quantum way and the potential advantages quantum technologies can provide for our application. So here we have 3 essential parts. The first one is the network's graph structure, showing the influence factors and the dependencies between them. So here we have an extract of our Bayesian networks to model the physics of the milling process. And we see here, for example, some jerks corresponding to certain axes. We have cutting forces, we have deviations, and we have, for example, the workload of the spindle. And these nodes within the network are equipped with some parameters. So we can consider in a very simple binary case, for example, a certain variable corresponds to hold a given tolerance threshold or even not. And the dependencies between the influence factors can be modeled with conditional probabilities, which are stored in these conditional probability tables. And these parameters can be trained using machining data. And for this purpose, we use the data from a digital twin of the milling process to apply such parameter learning algorithms. And the last part is about the estimation of the strength of inferences. And we use the learned parameters to do the analysis of strength of inferences by considering the changes in the probabilities of the dependent node when setting evidence to the influencing factor. This basically means we fit the value of a parent node to certain fixed status and watch at the differences in the probability distributions and construct a score based on a weighted sum method. So what about quantum computing to use in this application? We have especially in the context of proceeding inference, which we need to estimate the strength of inference scores. This requires a very high computational effort in Bayesian networks with a large number of nodes. And the two main characteristics of the qubits, such as the superposition and entanglement, offer an opportunity of a very compact representation of Bayesian networks. And the technology of quantum computing therefore features a method to handle especially large-scale networks, as well as to consider multiple structuring approaches in parallel. And this way, we are basically tackling a probabilistic model, which the Bayesian networks are, with a probabilistic computing architecture. And the goal now is to create a quantum algorithm and a corresponding circuit to encode the network and estimate the strength of influence. So some notes to the first part, the encoding part. Here we use the superposition principle of the qubits to store the parameters in the qubits. We have the amplitudes in the superposition state correspond to the likelihood of measuring the appropriate basis states via rotation gate. We can encode the nodes parameters in the corresponding qubit, which is indicated here as the map to the table. And here we have to mention that we are using IBM superconducting quantum computers, which are underlying the gate-based quantum computing model. And the same principle applies not only for the simplest binary case, but also for registers of qubits. When we need to encode more than 2 stages, then we need log n qubits to encode n different stages of a variable. And to model the dependencies or the conditional probabilities, we need multi-controlled rotations which encode the parameters depending on the parent node's status. And now, the missing part is about the distance estimation. So we finally need a tool to measure changes in probability distributions. And here, the commonly used technique of the swap test comes to the rescue. The swap test states the certainty of 2 quantum states to be different and can therefore be used to determine the distance between quantum states, which include the node's probability distribution. If we measure the bottom qubit, we receive the distance estimator similar to the classical way, but here now by reading out the 1-state amplitude of the bottom qubit. And now I want to hand over back to Jörg for the concluding part. He will finish with some statements about potentials and advantages the quantum way can offer in this manufacturing application.
Yes, thank you very much, Max. for this technical presentation about Bayesian networks in the quantum realm. And now we want to have a look. So what does it bring? And you have seen, you code this probability information that you have, those probability tables that you have in Bayesian networks in form of qubits. And this is also known from other application cases that this can be quite efficient. And basically, there's a logarithmic scaling. So you just need logarithmic number of qubits in the number of those entries in the table. So this is quite nice. So there's a memory advantage. Memory complexity is better. In the runtime complexity, unfortunately, you don't really see this because you have to encode the data. Max did explain this, how you do this with the different gates. And there may be actually the potential for further speed up. If you use amplitude amplification, you can go a step further and have this a bit more compact. And yeah, basically what we have done is a proof of concept at this point. And we want to go a bit further to look at larger setups and have a bit in-depth analysis about this. And of course, those speed-ups that I was talking about, we want to look at and want to implement. Let's again zoom out a bit further. So what we have seen in this example is, of course, what we want to have. And there are quite a few examples in the meantime where you have advantages either on the memory side or on the computational complexity side concerning runtime. And this is just a teaser for you. I don't go through those examples, but here you see that in many different technical applications, different algorithms, there's some speed up due to different reasons. The reasons are given here: amplification or the APHL algorithm, use of adiabatic quantum computing, or quantum RAM. And you see also a few citations where this is the case, for instance, for convolutional neural networks, different types of neural networks, support vector machines, and other applications. Okay, and this gives us basically our view, and that's what we want to further investigate. So thank you very much for your attention. And this here is actually a list of the 4 institutes, Fraunhofer institutes again, and the persons involved. So again, thank you very much. And I think we have maybe time for 1 or 2 questions. And if you want, also have a look at our brand new homepage.
Thank you so much to both of you for this interesting talk, in detail talk about the algorithms here for improving the accuracy, the parse accuracy in manufacturing. I would be interested. So you have you're developing all those algorithms, those approaches. Are you actually testing them? Are you actually doing the experimental part too? Because I'm an experimental physicist by education, so I'm always interested in the experimental part. Are you testing them on quantum simulators? Are you testing them on actual quantum computers that are available for first tries already by some companies and also by Fraunhofer now in the development, so to say? Is this a thing, or are you completely concentrating on the algorithm development part, on the theoretical part?
So we did some tests for some exemplary little scale examples using the real IBM quantum computers. And with the ability of the Fraunhofer group to also get tickets for the whole pool of the IBM quantum computers, we have booked a ticket for the upcoming month. And there we have planned to do larger scale investigations. On the one hand, with the simulators, just to check up the algorithms works, and then on the large scale real IBM quantum computers to see how this is today possible to implement on real quantum hardware.
Okay, very interesting. Thank you very much. Then our time is already over for this session. Well, let me see. There's one question just popping up just now. Is there a chance to map the problem to a quantum annealer? Maybe we have time for this one question here.
Difficult to answer. I think there is basically most of the problems you can solve on both types of machine. I would not immediately know how to do this because we have used specific gates, and we would have to look more deeply into this, I think, when there's a bit more time.
Okay, thank you very much. Of course, there's still the speaker's corner as with the others too. So for the next 10 to 15 minutes to the audience, feel free to engage our two speakers there. Thank you once again for your interesting presentation, and good luck with your further research on this.